Alrighty, thank you guys all for joining us. So I am going to talk about the oh-so-famous coding and algorithm interviews. But first thing, where I'm coming from. So I am a software engineer by training. So I was a software engineer for a while at Google, was on Google's hiring committee, did a far too much interviewing there, and then wrote Cracking the Coding Interview, which I'm sure many of y'all already have. And then another one for PM interviews. And then so I do now a lot of, in addition to the books and managing that process, I do a lot of consulting nowadays. So I do actually two types of consulting, both of which are kind of relevant to this. One is I do coaching for startups going through acquisition interviews. So when startups get acquired by big tech companies, they go through interviews much like a normal candidate. And so I get brought in by companies to prepare their engineers for that process. And so one of the things that's allowed me to do is get to actually interview the same person over and over again and see what kind of things help them perform better. And then I also do the other side and work with companies on how to hire engineers. So what I'm going to do today is talk about the kind of coding. I'm going to focus specifically on the coding and algorithm stuff and give people a framework for how to go through those kind of questions. But because people always ask, slides are online. Go to gayle.com, click on events. Actually, I don't think they're quite up yet, but you can find links to very, very similar slides up there. Or if you shoot me an email, g@gayle.com, subject to FB prep, coding prep, that'll give you a link back to the slides. Okay, so why are these asked? So contrary to popular belief, they are not puzzles, at least when done effectively. These are not puzzles, these are not tricks at all. The reason why they're asked is the sort of things companies are looking for. One piece is a strong foundation in computer science. That does not necessarily mean that you have to have a CS degree, although some of that knowledge may be tested. But it means that you want to be pretty comfortable with some of the foundational material. A big piece of this is looking at analytical skills, so problem-solving skills, essentially a fancy word for intelligence, at least as applied to a very, very particular type. Another thing is looking at communication skills. How do you make trade-offs? How do you think about things? I actually get a decent look at what is it like to work with you by asking these kind of questions. So although they're not true behavioral questions, I am looking at teamwork skills to some extent. Another big thing I look at is I like people who are really willing and ideally actually are excited about solving a hard problem. So some people I interview who I kind of describe as like mentally lazy, not necessarily stupid, they could actually be very bright, but they are mentally lazy. They have a mentality that any old thing is fine and it doesn't even have to be a good solution. As long as it's correct, that's good enough for them. And that kind of person worries me. I want to hire people who are really willing and ideally actually excited about solving a hard problem. So how do you prepare for these? The very first thing I put up there is assessing that you have a strong foundation in computer science. Again, it doesn't have to be a CS degree. You can learn the stuff on your own, but there is a foundation kind of knowledge you want to be very comfortable with. And this is what I'd say that the knowledge I expect people to have. So a few things I want to specifically mention here. TRIES, T-R-I-E-S, really common data structure for interview questions, so something that you want to be comfortable with there. I just mentioned that because a lot of people who do have computer science backgrounds don't know them because it's not something algorithms textbooks spend a whole lot of time on. But you want to be really comfortable with that. Big O, time and space, is a really, really, really important concept. And this is where I'd say the biggest delta is between where candidate really needs to be with the concept and where most people are at this point. So you want to be very comfortable with that. It's not just knowing the big O time of these different algorithms. Like, sure, that's a piece of it. But it's much more about when you see a new problem, you should be, you design a new algorithm, you should be almost always able to essentially immediately state the runtime. And then you make this or that change and you're able to state the new runtime. You want to be really, really comfortable with that. And then dynamic programming. What I mean by that is not memorizing specific famous dynamic programming problems. I'm talking about being comfortable with solving problems with that pattern. There's a lot of interview questions that are based in that, and something that it is dramatically easier once you've had some practice with it. So with your preparation, first thing I recommend you do is get very comfortable with data structures and algorithms, really mastering Big O. Practice on real interview questions. So I see a lot of people who try to prepare by reading algorithms textbooks, and sure, that'll develop your problem-solving skills to some extent, but ultimately, if the end game is to get better at solving interview questions, best to actually practice those. And then there's a lot of other people who think, okay, I want to get better at solving interview questions. And so they pick up Cracking the Coding interview and they just read it cover to cover. And that's not really practice. That's learning questions and answers, but it's not practice. You want to actually get better at solving new problems. And so you want to pick up an interview question and do everything you can to solve that independently. If you're using Cracking the Coding interview, yes, there are hints in the book, at least in the 6th edition, but don't pick up a problem and then read all 15 hints. Really try to push yourself and try to solve the problems independently as much as possible. Practice coding on pen and paper as well, or on a whiteboard if you have one. But basically, you want to be comfortable coding by hand. In many cases, at least, your interviews will be on a whiteboard. And so you want to be comfortable coding without syntax highlighting, code completion, all that kind of stuff. But actually, the more important reason why I really push people to practice coding by hand is that coding by hand is dramatically slower than coding on a whiteboard, or than coding on a computer. And because it's so much slower, you want to be comfortable coding in that, in a different way. So I'll make an analogy. If you're driving, now you're driving from here to some store 1.5 miles away. If you understand the basic just to how to get there, realistically, that's probably good enough. You might make some wrong turns. You might go 6 or 8 blocks out of your way. Not that big of a deal, though, really. If you are walking here to 1.5 miles away and you only know the basic gist and you start making some wrong turns and you go 6 or 8 blocks out of your way, you're going to waste a whole lot of your day. So as soon as people are on foot, they need to know, and they actually changes the way people think about it. You want to make sure you know exactly where you're going because it is so much slower and any mistake is a much bigger deal. Same thing with coding by hand. It is so much slower to code by hand, and so knowing the basic gist is not enough, and you really want to understand all the details. Mock interviews are also really, really useful. There are various mock interview services out there. You can use them. You can also grab a friend and just take turns interviewing each other. It's actually really useful if you can get some experience as an interviewer because a lot of the things that interviewers do, you'll just naturally do, and the process will make a lot more sense and possibly a little bit less intimidating to you. And then, as I mentioned, really, really push yourself through problems. Don't look at this as learning questions and solutions. It's really about learning how to solve new problems. So really push yourself through problems. But one of the first things up there that I mentioned is master Big O. So what I'm going to do is give you all a little crash course on Big O. So I know some people, I think a lot of people actually have some idea about what Big O is. It's a way of judging the efficiency of an algorithm. But there's a lot of mistakes that people make over and over and over again. And there's going to be a little bit of audience participation as well here. So first up, we have a for loop from I = 0 to n. What's the runtime of this? O of n. Yep. All right. Now we have 2 for loops, one going through evens and one going through odds. O of n. So I put this in here as a reminder. You always drop constants. You don't say O of 2n. OK. Now 2 arrays are going from I = 0 to a.length, and then within that, j = 0 to b.length. O of n squared is what everyone's saying that is totally wrong. O of a times b, O of m times n. P times q, x times y, whatever it is, 2 different variables. This is probably the most common mistake people make, and it causes a lot of problems. So when you say that things are n squared, or things are, you say that inserting into a balanced binary search tree is log n, it is not inherently log n. It is log n where n is defined to be the number of nodes in the tree. If n were defined to be something else, like the depth of the tree, then it would be O of n. N must have a meaning. Things are not inherently log n or inherently n squared. So the problem with saying this is n squared is that what on earth does n mean? N cannot be the length of the array if there's 2 arrays. You need to say O of a times b, O of m times n, something like that. So I see this causing a lot of problems in interviews. You'll have the problem I asked that I think I actually talk about a little bit later on, where you have an array of strings and you just sort the characters in each string. So sorting the characters first string, second string, third string, etc. And people will say, okay, well, gee, so for loop, so that's n things, then goes through all this everything in the array, n things, then you have to do sorting on all of them. So multiply that by n log n, so you get n squared log n, which is totally broken because those were 2 completely different meanings of n. What they should be saying is something more like, okay, sorting. Sorting is s log s, where s is the length of the longest string. Then you do that for everything in the array, let a be the length of the array, you get a times s log s. Be very, very careful for this. One thing I often recommend people doing is just if there's any ambiguity about what n might mean, just don't use n at all in the problem. Use something else that makes sense for that problem. So like W is the number of words, P is the number of prime numbers, whatever you need, but stop using n all over the place. All right, next example. We're going through from I equals 0 to n. Within that, j equals I to n. N squared. Yeah, so this is a pattern that a lot of people know. And then there's a good, another 20% people, I think, usually who don't. So when in doubt, you can always fall back on walking through your code. So the first time we hit j, we go from 0 to n, then 1 to n, 2 to n, 3 to n, 4 to n, 5 to n. So we're basically printing half of a grid, but we drop constants, so we get n squared. All right. Now we have a little bit more complex example. So here we have an array of people with their birth years and death years. And the question is, how would you find so the population is going to change over time. How would you find the highest population over all time? So this is kind of a brute forcey approach, but basically we are going through each person, getting the very last death year. Then we are creating a histogram from year 0 to the last death year, walking through each person, walking through each year they're alive, incrementing that value, and then getting the biggest value in that histogram. So let's take this piece by piece. The first step, that just walks through each person. What's the runtime of that? Yeah, O the number of people, so I'll let P be the number of people. And then second step, walks through each person, then walks through each year that they're alive. Yeah, so P times you have to be very careful. A lot of people will think P times the number of years, but what number of years? The number of years that the galaxy was around? What number of years? Specifically, it's P times the max lifespan. Then third step is walking through from year equals 0, year less than counter.length, year plus plus, getting the biggest value. And what's the runtime of that? So I know from past times I've done this. Statistically, a good number of people are thinking about O of y, because hey, it's a for loop that goes through years. Y means number of years. Yeah, but totally different number of years. Y is actually a lifespan, like 80 years. This for loop goes through to the very last death year, which is something like 2016. Very different values. So we just use a new variable for that. Let L be the last death year. And then we get P times Y plus L. So a few common mistakes people make, that I kind of mentioned. Seeing step 3 and jumping to O of y. Be careful for what your variables mean. I'll also see people often in step 2 describe that as P plus Y. And I think most people understand that is P times Y, not P plus Y. But I think people just, in the heat of the moment, aren't really thinking clearly. So be careful when you add and when you multiply runtimes. Also see people do things like, oh, and L is a constant, or P times Y is bigger than L, so we can just drop that. And no, there's no particular relationship between P times Y and L. Just got to include them all. You can drop this first P times 1 in that sum, because P times Y will be bigger than P times 1. OK, new example. Now we have an array. We're going through each value in that array and calling validate on that.
In the previous question, the complexity won't be big O P into Y. It can't be neglect L.
What's that?
It can't be neglect L. The complexity won't be P into Y.
Why can you drop L?
Because L is L is a linear function and that's a exponent.
But it's linear on a completely different thing, right? P times Y is not necessarily bigger than L. It's linear. Like if it were n squared plus n, yes, you could drop n, because n squared is bigger than n. But P times Y is not necessarily bigger than L, right? You could have 5 people and 80 years, and we're talking about millions of years in the future. There's no presumed relationship between them. So you just got to, when in doubt, include them all. Unless you can prove to me that P times Y is bigger than L. OK, so array, calling validate on each element in the array. Depends on the value of validate. I think pretty much everybody looks at that and kind of knows something's up, because I haven't said what validate does. But then there's like a portion of people who look at that and are like, well, I don't really know what this validate thing is doing, so I'm just going to ignore it and call this linear. It doesn't work that way. Just because you don't know what a value is doesn't mean you can just ignore it. So best answer is probably undefined, you don't know, depends on validate, whatever. if you were in an interview and you said it's n times the big O time of validate, I'm fine with that. It's a little bit, to me, that's a little bit awkward because validate could actually be another operation that runs on O of n time or runs on some other random variables. I'm not too concerned if you say that, though. But you certainly cannot say just O of n. OK, recursion. This is where a lot of people get stumped. So here we have a linear, or we have fib of n, and we call fib of n is if n is 0 or 1, we return 1. Otherwise, we return fib of n minus 1 plus fib of n minus 2. What's the runtime of this one? So here are a couple of things: log n squared, n factorial to the n O of n. So when in doubt, you can always fall back and walking through your code. So suppose I call this for fib of 6. Fib of 6 will call fib of 5 and fib of 4. 5 will call 4 and 3. 4 will call 3 and 2, and explode into this tree. So if I call this for, say, fib of n, how many levels are in my tree? No! Trees are not inherently log n height. Like when you say trees are height log n, that is only true if n indicates the number of nodes in the tree. If n indicates the number of stars in the galaxy, that's not log n. Be very, very careful of this. And in fact, I used to ask this question as, expressing it as fib of k, and people didn't make that same mistake. Not as often anyway. The variable naming actually throws people off. So this is not height, that's not height log n, it's height O of n. Because the tallest path in that tree, longest path, is at fib of 6, fib of 5, fib of 4, fib of 3, fib of 2, fib of 1, fib of 0. That's an O of n height path. So there are n levels in my tree, roughly. First level has 1 node. Second level has 2 nodes. Each node has 2 children. So 4 nodes, 8, 16, et cetera. So if I take 1, I do times 2 times 2 times 2 times 2, and I do that n times, what do I get? 2 to the n. Great. What's my space complexity? O of n. Excellent. A lot of people will say 2 to the n. So space complexity is another term for memory usage. The way that I like to think about this, or the way that I find it easiest for most people is, if I gave you a chunk of memory and I said this is all you get to run your program, how big would that have to be? So yes, all 2 to the n things, so the call stack is really important here, right? And yes, all 2 to the n things do wind up on the call stack at some point in time, but they're not all sitting there at the same time. So you don't need O of 2 to the n memory to hold the call stack just because at some point over all of history, 2 to the n things wind up there. You only need the amount of memory that the call stack actually uses at any one point in time. And the call stack only grows linearly. It goes through that longest path. That's the tallest path it gets, or longest, most number of nodes on the call stack is that longest path of 6, 5, 4, 3, 2, 1, 0. So we only need O of n memory for the call stack. And this is, of course, a very, very inefficient way of computing Fibonacci. And the reason why this is so inefficient is we keep repeating work. We compute fib of 4 twice, fib of 3 times, fib of 2 5 times. It's always the same thing, right? Fib of 3 is not sometimes one value and sometimes the other. So what we should be doing is saying, compute it once, and if I ever need it again, just store it and give it back next time I need it. And that's what the most basic memoization example is. A lot of people struggle with memoization, and the vast majority of memoization problems are really just twists on this. It's the same kind of framework and pattern. Once you get very comfortable with it, it's actually very easy. So here we use a memo table. In this case, just an integer array. In another case, we might use a hash map or hash set. Basically say, OK, if we haven't computed mem of n, compute it, store that value, return the stored value. Now what is my runtime? O of n, yeah, because this is what my call tree looks like here. I still have n levels in my tree, but there's a constant number of nodes at every single level. So we're going to have O of n nodes in my tree. And so that's going to give a runtime of O of n. And then what's my space complexity? O of n. Yeah, my space complexity, I still need O of n memory for the call stack. I also need O of n memory for my memo table. But O of n plus O of n is O of n. OK, so keep an eye out for these kind of problems with these kind of issues with big O. Do drop constants, but don't drop things that aren't constants. Be very sure that you have a good justification for when you can drop things. And you can look up a more academic discussion of when you can drop things, when you can't, but make sure you have a good justification. Remember that you can use different variables. One thing that throws people off in big O a lot is they have some array as input, and they're only thinking about things in terms of the length of the array. And then they have something else going on in the problem, and then they don't know how to handle it. You can use whatever variables you want. If you need a variable to represent the number of prime numbers in some array, you can use that. If you need a variable to represent the biggest number of that array, you can use that. So you can use different variables. Be careful about throwing around n everywhere. If there's any ambiguity about what n might mean, just don't use n at all in the problem, and it'll save you a lot of problems. Be careful when you add and when you multiply runtimes. Again, I think most people fundamentally understand this. I still see it cause a lot of problems. And then when you see recursive problems, especially recursive problems that take multiple branches, so like Fibonacci takes the n-1 and the n-2 branch, as opposed to like searching in a binary search tree, which goes left to right, but it doesn't go to both places. When you see something that takes multiple branches, that's when that called tree approach is really, really useful. So draw out that call tree, look for the repeated subproblems, or draw the call tree. That'll generally give you an exponential algorithm. See if there's repeated subproblems. More often than not, in an interview context, there are. And then see if you can cache those. And when in doubt, you can always fall back on just walking through what your code does and trying to derive the runtime from there. All right, so that's my crash course on Big O. And now I'm going to switch and talk about how to actually solve problems. But just before I go into that, I want to talk about evaluation. So when we ask you problems, at least if you have a good interviewer, it's not a quiz. When I ask you, design the algorithm to select a random node from a binary search tree, this is not a quiz. I'm not asking you what is that algorithm. My assumption is that you don't know it, you don't know how to solve it, because you've never heard the problem before. If you have, let me know. But my assumption is you don't know how to solve it. And you will probably spend a while struggling with it. And when you write code, you probably won't write perfect code. Right? It's just like in the real world. When you get thrown some hard problem in the real world, you aren't just like, aha, and brilliance comes out and you like write everything perfectly, right? And it's also not like perfection isn't better than lack of perfection. Of course it is. But you don't get fired because you're not perfect. It's the same thing in interviews where like people don't, these flawless interviews don't really exist a whole lot. They're very, very rare. Pretty much everyone is struggling with the problems. What I do want to see is that you're excited about problems, that you're really willing to drive through and get to a great solution. I want you to keep trying, even when it's hard, even when you're struggling, even when you're kind of stuck. Keep trying to make progress. Problems are hard, and that's fine. Just because you're struggling, you can be struggling and still be doing very, very well, because you could be struggling less than everybody else. Coding. Generally, interviewers, when in doubt, interviewers are not okay with pseudocode. They do want to see real code. That said, understand what an interviewer is, or at least should be evaluating. It's not, interviewers are not sitting there like looking at your code, taking a snapshot of it, running back to their computer, and then like typing up verbatim and then saying, okay, if it doesn't compile, if it breaks, if it doesn't compile, if it has a bug, whatever, then you fail. And that's not what's going on. What's happening is interviewers are taking your code as a code sample and looking at it saying, okay, what does this tell me about your coding skills? If you're using Java and you call some method, you write list.insert, and in Java it's actually list.add, my conclusion from there, technically speaking, the code breaks, right? But my conclusion of that is you don't use Java's linked list class a whole lot. Is that an issue I care about? Not at all. If somebody else I interviewed not long ago he had quite a bit of a coding experience. He wasn't a newbie at all. And he was mixing up single equals and double equals. Not a typo. Right? I've had that typo happen before, and that's fine. Not an issue if it's actually a typo, but he still didn't quite understand assignment versus comparison. That is just a compilation error, but it's indicating a whole lot to me about your coding skills. So, it's not, does it work, does it compile, does it have a bug, whatever. It's what is this telling about your skills. That said, if you can write more perfect code, that's obviously a good thing. Likewise, when it comes to your problem-solving skills and like the speed at which it takes you to solve a problem, all that kind of stuff, I'm not sitting there with a metric that says, okay, if you get to the problem, if you solve the problem, you have 20 minutes to solve the problem, and if you do that, thumbs up. If you don't do that, thumbs down. It's all about, what is this telling me? You can take 15 minutes, and somebody else can take 10 minutes on the same problem, and you can do a lot better. Because the reason why that other person took 10 minutes is because they were actually really, really struggling, and I gave them a whole lot more help. They clearly did worse, even though, yes, technically, they got to the optimal answer faster. They only got it faster because they got a bunch of help along the way. So, all these things, it's not, did you solve the problem in this number of minutes? It's all, what is this telling me? What is the speed at which it took you to solve the problem? What is your ability to have picked up on some of the hints being given? What does that indicate about your problem solving skills? So the best thing you can do here is just expose your thought process as much as you possibly can. I cannot give you credit for that great insight you had if you didn't voice it, right? And I can't, and even worse, I might think that you're stuck when you're not, and think you're totally stuck, spinning your wheels. I might jump in then to give you a hint that you don't actually need because you already knew that if you're not talking out loud. So try to expose your thought process as much as you possibly can. Some concrete things you can do here. First of all, practice this. Lock yourself in a room, or better yet with somebody else in there, though I wouldn't recommend locking the door then, that's creepy. But get yourself comfortable with talking out loud. Even if your audience is completely non-technical, it's still just comfort with doing that. Try to, when you're practicing as well as in the actual interview, anytime you notice yourself being quiet, try to take a step back and give me at least a headline of your thought process. Try to tell me, okay, what I'm thinking about right now is how to optimize this piece of code. What I'm thinking right now is that it seems like there's something we should be able to do with the arrays being sorted. So try to give me at least a headline. And then at that point, if you can, I want to be very clear, if you can perfectly clearly articulate your thought process, that is fantastic. But if you're choosing between mumbling and saying nothing at all, mumble, right? I've probably asked, a dozen or two people to solve the same problem. Mumbles actually give me some idea of where you are in the problem. It's something. It's better than nothing, right? Great communication is fantastic, but if it's just periodic headlines with mumbles, do that rather than doing nothing. Okay, so actually I talked about this stuff. So what I'm going to talk about now is how to solve problems. So I'm going to walk you through this kind of structure for how to solve a problem, and the contrast is really out of whack here. But you can find this at crackingthecodinginterview.com. Click on resources. Actually, I have the wrong auto response up, but it doesn't really matter. Or you can shoot me an email, g@gayle.com, with the subject coding prep, and that'll give you a link back to the slides. I also actually, right outside the door, have some old giveaways that I happen to bring today that have kind of like a mini version of this stuff. But this is basically a framework for how to walk through problems. So I'm going to walk through what this is today. First thing is listen carefully to the problem. So it's a good rule of thumb that every bit of detail given in the problem is necessary. So if I tell you that, example is you have two arrays sorted and distinct, compute the number of elements in common between the two arrays. The sorting piece, let's think about that. You can compute the number of elements in common between two unsorted arrays. You don't actually need the arrays to be sorted to solve that problem. So why did I make the arrays sorted? Well, because the more optimal answer hinges on that. So assume that every piece of information given the problem is really relevant and useful and changes the solution in some way. I'll give another example of this. So anagrams. So the definition of anagram is a permutation of a word that is also a valid word. So the anagrams of rates are asterisk, stare, taser, and tears. So the question is, how would you build an anagram server or website? So you're going to basically get some list of valid English words, and then you want to spit out, anytime someone enters in a word, spit out all anagrams of that word. So I used to ask this problem a bunch, and I'd see a whole lot of people who would design these functions that basically took in a word, permuted, computed all permutations of that word, checked each one against the dictionary, and then spit out the result. And then they would kind of, as an afterthought, basically say, oh, yeah, it's on a server, right? It's going to pull it up from disk or whatever. They're not really making use of the server piece in any good way. The algorithm is operating essentially equivalently as if it weren't on a server. So if that was all I was expecting, why would I put it on a server? The server piece logically is probably doing something more interesting or more useful. So what does a server let you do? Well, it lets you do caching, repeated calls. It potentially gives you access to databases and things like that. One of the things it lets you do is pre-computation. And in fact, if you look at this list of anagrams, the characters in each of these words sort to AERST. And what that means is you can take, in this pre-computation step, when your server boots up, take all the words in the dictionary, sort the characters in every single word, and build out a mapping of the sorted version of a word to each word that's sorted to that. Then when someone says, give me the anagrams of rates, you just need to pull out the ARST grouping. So the server piece is useful. So assume that when you get some problem, every piece of information given that problem is useful for some good reason. Second step is to draw an example. So think for a moment about what you would draw up on the whiteboard for that previous problem, which was 2 arrays, sort and distinct, compute the number of elements in common between the 2 arrays. So pretty much everybody, well, 70% of people, draw an example like this. So 2 elements, 4 elements, 2 arrays, same size, right? Technically it fits the problem, but it's not a very useful example. This is a more useful example. Much larger, multiple elements in common. The idea here is to make your brain do work. So you can, when I put this up on the board, on the projector, you can probably notice your eyes darting around to try to match up the elements. That is an algorithm of sorts that your brain is doing. It is something that's helping you understand how to solve the problem. When I put this up, there's nothing you got to do. As soon as you see those 2 things, you notice there's a 12 in common. You didn't do anything, it's glance and it's obvious. So make your examples complex. Make your brain have to do work. If there's any special cases you drew in, fix those. So if you do these as the same length arrays, fix that. There's no reason to believe they're the same length, so don't draw them as the same length. So try to make your examples large and as generic as possible. Third thing is a brute force or naive algorithm. Stupid and terrible is fine as a starting point. So that's not to say that if you get some problem and you happen to come up with a fast one off the bat, that you should go out of your way to first come up with something slow. No, not that. But if I ask you a question and the first thing you come up with is something really slow, that's fine as a starting point. Go ahead and state that. Sometimes people will think they want to make sure their first algorithm is a good one, so they just say nothing at all until they have something good. And the problem there is, one, if you misinterpret the problem, you could spin your wheels for a long time before we figure that out. At least if you state some algorithm that makes no sense, we can correct that misunderstanding now. If you don't state it, in fact, this happened years ago when I was a candidate interviewing. I got some problem, and there was a brute force that was really, really obvious, and so I just didn't say anything at all because I figured everybody knows that. And several minutes later, the interviewer finally jumped in to say well, you can at least do it this way. It's well, of course I knew that. And now looking back on it, I know being an interviewer that unless I said that, they don't know that I know that. So if you don't state that brute force, as far as I know, you're not a strong enough problem solver to come up with this thing that's obvious. Which is not to say that brute forces are always obvious. They're not. But if it is obvious, if you come up with it, go ahead and state it. And the other thing is that it's often a pretty useful place to optimize from. So, and other thing I want to be very clear about here is I want to be very, very, make sure you understand this. I'm not saying to code the brute force. I'm saying I asked you a question, you make sure you understand it, probably write an example. Sometimes you say to brute force first, but either way. And then you state the runtime, and then you start talking about optimizations. Generally speaking, you're going to spend a lot of time on optimizations. It's a really core part of the problem. And you do that before you start coding anything. So do not code unless you're sure that is what I want you to see. Don't code and then think you're going to optimize later on. The optimizations you're going to make are huge algorithmic changes. You don't have time to write something and then rewrite everything. So state the brute force, state the runtime, and then talk about optimizations. So I'm going to spend some time talking about different ways of optimizing and solving problems. So first one I want to talk about is called BUD. And BUD means to walk through your algorithm and look for bottlenecks, unnecessary work, and duplicated work. So bottlenecks. So you have we'll go back to this problem, 2 arrays, sort and distinct, compute the number of elements in common between the 2 arrays. Brute force algorithm, start with 1, walk through second array, look for 1s. 12, walk through, look for 12s. 15, walk through, look for 15. What's the runtime of that? Not n squared. A times b, m times n, something like that. So this O of b is a bottleneck. For every element A, we're doing O of b work from these continuous. Is there a 1? Is there a 12? Is there a 15? So what's a faster way we can do that? Yeah, it's sorted. So we can do binary search. So that gives an A log b algorithm. Log b is still kind of a bottleneck in that problem. So we could also, somebody else I heard mention, take everything in B, throw it into a hash set, and that'll give us an A plus B algorithm, but O of B space. One thing that's interesting here is I had made a big point in step 1 of like, everything's given for a reason, every detail is necessary with the problem. An O of A plus B algorithm is what I define sometimes being the best conceivable runtime, which is to say that you cannot possibly design an algorithm that is better than O of A plus B, because you have to touch every element. And yet, this algorithm with the hash set is O of A plus B time, but doesn't use the sorting piece. You know what I'm saying? Like we're as optimal as we could possibly be, but without using some information. So what happened? Well, what happened is that we are as optimal as we could possibly be with runtime, but not with space. So we have an O of A plus B time, but O of B space. So when we think about optimizing this further, the bottleneck is actually really the space thing. That's the thing that's hurting us, hurting our efficiency. So we want to get something that uses less space. And what we can do is we can walk through A and B with 2 pointers, kind of like if we were merging 2 sorted arrays. And that'll give us an O of A plus B time and O of 1 space. And that'll be the most optimal thing we can do. So in your solutions, identify if there's a bottleneck and really focus on how can you get rid of that. Second thing you can look at is unnecessary work. So new problem. You have the equation a cubed plus b cubed equals c cubed plus d cubed. Find all solutions to that where a, b, c, and d are integers between 1 and 1,000. So stupid, obvious, terrible brute force here. Walk through all solutions for a, b, c, and d. Check for matches. Really slow, but it'll work. And by the way, this is not a math problem at all. There's no weird factorization here. It's just a straightforward algorithm. So we can make this a little bit faster by throwing a break statement after that print. Doesn't change the big O time. Our big O time will still be O of n to the 4th, but might as well do it. With that should make us think, is there a better way we can do it then? If there's only one value of d that works for any given a, b, and c, can we find that d more quickly? Like if I told you, a is 17, b is 101, c is 53, and then I asked you what's d, and I gave you a calculator, I don't think you would actually plug in d equals 1, d equals 2, d equals 3, d equals 4 until you got to the right value. What would you do? Yeah, subtract out, so solve for d. So d is the cube root of a cubed plus b cubed minus c cubed, so you'd solve for d. So pay attention to these little optimizations, like just throw in a break statement here. A lot of times those do not change the big O time in and of themselves, but linked with some other thought, they actually might. So pay a little bit of attention to them. Don't totally dismiss them. Third thing is duplicated work. So if we go back to this brute force, what this is saying is basically walk through all AB pairs between 1 and 1,000. Then for every single AB pair, walk through all CD pairs between 1 and 1,000 again. So this CD work is being done over and over and over again. So for every AB pair, we're walking through all the CD pairs. So one thing we can do is say, okay, we're doing this over and over again. So actually just generate the list of all the CD pairs between 1 and 1,000. Then for each AB, we'd want to just look up matches from that. And specifically, we're matching over the a cubed plus b cubed result. So build out that hash table. Map from a, oops. Yeah. So build out this hash table that maps from a c cubed plus d cubed to each pair that got us that same integer. Then for each AB, pull out the matches on the hash table. So notice when you're doing work over and over again, oftentimes that's an optimization. Okay, next thing, space-time trade-offs. A huge portion of problems involve hash tables. So it's kind of a really lame joke, but in interviews, use hash tables just constantly. Like a huge portion of problems involve hash tables. I mean, don't just throw it out for no reason, but any given problem, recognize that there's a good 50% chance that, at least 50% chance that it's going to involve a hash table. So have it at the top of your mind. So here's one example with a hash table. Find the number of pairs of values with the find some sum. Find the number of pairs of values that get to a particular sum. So we could build out a hash table that by taking all of those elements, throwing them to a hash set. And then we're saying find all pairs that sum to 7. Well, when we have a 5, we want to basically see, hey, is there a 2 in that? And we can use a hash set for that. So have hash tables at the top of your mind. Pre-computation is another type of space-time trade-offs. So new problem. You have a matrix of positive and negative values. How would you find the submatrix with the largest sum starting at the top left corner? So what is, well, it'd be too hard to do this, but a really, really, really terrible way of doing this, if you want to find the submatrix with the largest sum, starting at the top left corner, is walk through all possible values. In fact, pretty much any problem framed as a find the biggest this, find the smallest this, can be solved that way. So that would mean get the sum of 6, then 6 plus 5, then 6 plus 5 plus negative 9, 6 plus 5 plus negative 9 plus 2, 6 plus negative 2, 6 plus negative 2 plus 5 plus negative 5, et cetera, et cetera, et cetera. Adding up all the elements. And what you might notice is that as we're adding up these 9 elements here, that requires adding up, well, these 6 elements on the left in that blue outline. And that's work we've done before, so we don't have to re-add those things from scratch. The green outline has also been added before, and that'll give us the negative 9, negative 2. So we want to get the sum of all those orange elements. We can take the blue outline. We've done that in the past. Green outline, also done that. But now we're double counting those red elements in between. We've also added that before. So if we double counted it, we don't want to double count anymore, take it out once. Then add on that last element left behind. So pay attention to space-time trade-offs, using more space to save yourself time. And have hash tables and pre-computation as a general technique that you might use in problems. Third thing is one that I probably use the most, is what I call do-it-yourself. So new problem, you have 2 strings, one smaller, one bigger. Find all permutations of S within B. So I see a lot of people in this problem who will find all permutations, will go down this path of generate all the permutations of S, search for every single one within B, which is fine as a starting brute force, but how many permutations of S are there? S factorial, yep. You do substring searches on every single one. So we're talking about a runtime that, if we're lucky, is S factorial times B. That's really, really, really bad. And I'll see a ton of people here who will be like, okay, well, let me take B and throw it into try. Maybe that'll allow me to do a faster substring search. Maybe I can get down to S factorial times B, which is still terrible. Right? At that point, it doesn't really matter. S factorial is so incredibly slow. If you think about n factorial versus 2 to the n factorial is way worse. Because we always think about 2 to the n as being terrible, but n factorial is way worse. Because both are n things multiplied together, but at least for 2 to the n, they're all 2's. Factorial is really, 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 really bad. That's, if you think about this bottlenecks thing, that's where your effort should be in. You come up with this S factorial times B, focus on cutting down that S factorial time. So where we should have really started is with an example. So here's an example. So where are some of the permutations of S within B? Or where's one of them? First 4 characters, yeah, B, A, B, C. Where's another one? B, C, A, B. Last 4, A, C, B, B. C, A, B, B. Pretty much everyone can do this. There's a whole bunch of them. I think I even missed one there. But pretty much everyone can do this. Not too hard. And what's interesting here is I'll do this in interviews, and people will swear that you have to generate all the permutations of S in order to find them. And they will swear to me you absolutely have to do that. And then given an input, nobody out of dozens of interviews has ever actually done that. People consistently swear that their algorithm must do that, and yet they are consistently able to do it without doing that. Nobody, even for a tiny little string like that, nobody writes down all 12 permutations and then looks for them. Everybody pretty much does something like walk through, I can actually come to the board. Walk through B in windows of size S, sliding this window along like this. And in fact, if you look at the way people shout out answers, you can tell people did the same thing here. Because the first ones was the first 4, and then the next one came, and the next one, next one. Pretty much everyone does something like that. And this happens for a lot of problems. There's a lot of problems where, in the context of interviews and algorithms, things like this, people will come up with this really slow thing or just be very stuck or whatever. But then given a really big input, and they're just asked to just solve it, get the output manually, whatever it is, and however they go about it, they come up with their brain finds a pretty good way of doing it. So what you need to do is make your examples large, and then think about trying to reverse engineer what exactly your brain did, and try to get the algorithm afterwards. Fourth thing is solving things incorrectly, which sounds a little funny. But what this means is basically when you have a problem and you can't come up with anything that's fast or correct, come up with something that's incorrect and see if you can make it correct. So, problem I often ask people. You have a binary search tree, and you're actually going to write the class from scratch. so you have access to whatever you want. How would you add a method to that algorithm called select random, which returns a random node from the binary search tree? So what a lot of people start off with here is this technique of, okay, well, flip a coin, heads goes left, tails goes right. Does that work? And then when you get down to the bottom, return that node. Does that work? No, because it's not going to give you, I mean, you're not going to return any of the earlier nodes. The root will never get returned, so that's not really random. Okay, so the problem here is the root never gets returned, so let's fix that problem. That means maybe we could do something like this. Select a random number, 0, 1, or 2. 0 goes left, 1 returns the root of that subtree, and 2 goes right. Does that one work? How often will what's the probability of returning the root? 1/3. Do all the nodes have 1/3 probability? No. So that's not going to be random. So the problem here is that the root cannot have 1/3 probability unless there's 3 nodes in the tree. The probability we need to return the root with is 1 over n, where n is the number of nodes in that tree. That has to be the value in order for them all to have the same probability. So one thing we could do is return the root 1/n probability, where n is the number of nodes in that subtree. If we don't return the root, flip a coin, heads goes left, tails go right. Does that work? Imagine I mix up the tree a little bit. Imagine the tree is this. So I return the root with 1/7 probability. If I don't return the root, flip a coin, heads goes left, tails go right. Now, 60 is going to have a wildly skewed probability. 60 is the one on the right. We'll have a wildly skewed probability. So the problem is we are going left as often as we're going right, even though we might have dramatically different number of nodes in the tree. The probabilities we need to get here is 1/7 of the time we need to return the root, 1/7 of the time we need to go right, and there's 5 nodes on the left, so 5/7 of the time we need to go right or left. So that is a different algorithm. So pick a random number between 0 and the size of the subtree, turn root 1/7 or 1/n of the time, left 1/n or left size divided by n times, right the other times. That will give us a proportional probability. So when you don't have a correct algorithm, start with something that's not correct, and then figure out if you can figure out exactly what makes it incorrect and see if you can fix that. Okay, so those are the techniques I use a lot to solve problems. The mistake that a lot of people make at this point is they basically understand the gist of what they're about to do. And they get this algorithm, pretty much works, they'll feel okay with it. And then they try to start coding it, and they kind of skip a step here. And that's walking through it. So people code prematurely all the time, and it causes huge, huge, huge problems in their code. If you don't know exactly what you're going to do, you're going to write very much the wrong thing, right? It's like walking out to that store when you only understand the basic gist. And that's not a big deal if you're in your car, because not a big deal to walk a few blocks out of your way. It's a really big deal when you're on foot. Same thing with coding. Take a step back and walk through your algorithm on your example. Make sure you know exactly what you're going to do before you start coding. When it comes to coding, think about your goal as fundamentally about writing beautiful code. Some people think about I want to get correct code in interview. No, your goal here is use these 10, 20 lines to prove to me that you're a good software engineer, which is not just about correctness. So some tips on writing good whiteboard code. So modularization, talk about that in a little bit. Think about error cases, to-dos, things like that. Even if you don't write them in line, at least discuss what they might be. Use good style, variable names, etc. One of the mistakes that a lot of people make is they walk into whiteboard coding things with this attitude of well, it's just a whiteboard, so it doesn't really matter if my style's bad. And the problem is that I cannot distinguish between you wrote with bad style on a whiteboard because you write with bad style in general, versus you write with good style normally, you just were lazy on a whiteboard. If I could distinguish, great, but I can't. So when you use bad style, that's potentially indicative of an issue to me. So use good style, be consistent. You can, it's a pretty solid idea to adhere to some well-known style guideline, not because I'm checking you against that, but because that happens to be pretty good style normally. A couple of things. So little things, try to write straight on the board. Seems kind of silly. It is kind of silly, but what I see is I see a lot of people who write with these like 20-degree angles in their code, and I'll actually be okay. Like I can evaluate your code just fine. But what I see is when people do that, they start to have trouble walking through their own code. So try to write straight. Give yourself, make your life easy. Give yourself as much space as you can, right in the top left corner, or wherever you have the most space. If there's stuff you don't need up on the whiteboard anymore, erase it. This is your board. You do what you want with it. If you run out of space, use arrows to insert code. Language choice is often up to you. Depends on the company, but it's often up to you. My major advice here when you think about what language to pick is use what you're most comfortable in. I see a lot of people who will be like, oh, I'll code in Java, or I usually code in Java, but I'm a little Java's so verbose on a whiteboard, so I want to write in Python instead. And then what they write up on the board is neither of the two. It's like 90% Python, like 10% Java, and now I don't know if they really can write syntactically correct code, and they're making other problems. So code in whatever language you're most comfortable with. If you're going to code in a language that is not your dominant language, really make sure you're putting that extra legwork to solidify your understanding of that syntax. Modularization. So I want to spend slightly more time on. This is terrible code. Do not write code like this. It is one giant function. And this is a function for a problem called the ransom note problem. But basically, it processes one string, processes another string, compares results. So this is the very first thing you should write. Don't write loose code. Write it always in a function. But the mentality I encourage you to have is when you start writing code, assume that you are in some magical language where like anything you could possibly want is built into the programming language off the bat, even things that obviously weren't. So modularize aggressively, call these functions that don't exist yet, and then start drilling in deeper and deeper and deeper and expanding those functions, writing whatever's the next most interesting algorithmic piece. Anytime you have a little conceptual chunk of code, pop it off to another function. So I need a thing that converts A to 0, B to 1, C to 2, pop it off to another function. Don't write that in line. It's one of the easiest ways. It shows good coding style. It means if you get cut off, partway through, you've written the most important pieces. You get out of writing really tedious stuff often. Because if you ask me before you write this last function, I might tell you not to write it. It's just it makes testing a lot easier. It just modularize aggressively. It'll make things so much easier. When it comes to testing, you do need to test your code. So one of the mistakes people make is they take their example that's usually still up on the whiteboard and they throw that in as a test case. And the problem is that will take them a really, really long time to go through. Also, if you use this example heavily to derive your algorithm in the first place, which you then wrote code against, and so it's not necessarily the best test case anyway. A better approach is first start off with just analyzing your code, walk through it line by line, think about every single line of code. Was that really the right thing? Anything that looks weird that might be, that's likely to cause bugs, double check. So you have a for loop that decrements instead of increments. Double check that code. You have a variable initialized length -1. Double check that. Any math, double check. Then actually I'll say one other thing here. One of the exercises I often give candidates in interviews or when I'm coaching them and they're having trouble finding a bug is I'll have them take a step back from their code and assign risk profiles to lines of code, like low, medium, high. And so not finding what the bugs are, but just saying which are the risky lines of code. The line of code that's like x equals process string of a comma b, low risk, right? Like how many ways could that line of code go wrong, right? The implementation of that could be wrong, but you could mix up the parameters orders. It's really hard for that to have a bug. The line of code that's like x equals a dot substring of I comma I plus k, that's high risk. It's not like it's super complicated, but was it I plus k, I plus k minus 1? Maybe it was like k over, various ways that could mess up. So double check the high risk lines of code. Then when it comes to test cases, start with small test cases first, not big ones. A lot of people start with big ones, and what happens is, one, it'll take them a really long time to walk through and find the bugs, because there's more things to run through, and manual testing is really slow. But two, what happens when people start throwing in these big test cases is they start to very quickly, that's the second, third element in their array or their test case, and they're like, oh my God, this is taking forever. And then they start getting very hand wavy. And they basically assume that they know how their code operates, and they assume that their code works, which kind of defeats the purpose of testing. So it doesn't work that way. You need to actually start with small test cases, much more effective than big ones, then throw in some edge cases, and then maybe a few times some big ones. When you're testing, make sure that you're actually testing your code and not your algorithm. I see a lot of people who will either not be looking at their code at all, and they guess they think that they're testing, but they're just walking through their algorithm again on their example, which is not testing. Or they'll be slightly better, and they'll walk through it, and they'll see this line of code that is like x equals a dot substring I comma I plus k, and they'll basically have the assumption of like, oh, that's the line of code that will give me this output. And so they'll assume it gives them that output, which again is not testing. Testing is saying, okay, I is 3, k is 2, so that's going to be a substring from character 3 to 5. So that'll be, double check that in the array, that'll be this thing. That is testing, actually walking through it at that detail. So test your code, not your algorithm. As you're testing, think as you're doing it. I see a lot of people who will test almost like they're a bot, and they just run through it, and then they get to the very, very end, then they'll see, oh, it has output of this instead of this. Now what? Right? The purpose is to fix these bugs, and you found it, but you don't know where the bug happened. And now you basically have to try to reverse your steps, which is almost impossible, or run through it again, and it's not a good experience. It'll take you a lot longer. And additionally, just because you got the right output doesn't mean you didn't have a bug along the way. It's much more effective if you look when you get that, you do that x equals a dot substring I comma I plus k, and you get that, that gives you a result of, qpx. Is that the thing that was actually expected to happen? Is that what you needed there? So think as you're testing. And then when you find a bug, think before you fix it. A lot of people will, I guess they have this attitude that they want to get their code correct as fast as possible. And so they find a bug and they jump in and try to make a really quick fix. And it fixes it for that specific test case, but it wasn't the real bug. So there's the code for that substring problem where you're sliding that window of size s along. So you don't want to slide that window off that big string. So most people write code that's like for I equals 0, I less than b dot length minus s dot length, and that's actually a bug. Almost everyone writes code just like that, but is actually a little off by one error. It should have been b dot length minus s dot length plus 1. And what happens is people throw in a test case when b and s are the same length, and that's when they find the bug. And so they make a fix that fixes it for that one specific test case, but not for the real bug. So when you find a bug, it's not that big of a deal. Most people have bugs in their code, in the real world as well as in interviews. But when you make the wrong fixes, that's a lot more dangerous. Because when you do that, we think it's fixed. We ship your code. We close out that bug report. We think it's good to go. But then in reality, bug is still there, just not for one specific test case. Bug's still there. You have added new code that makes our code base more complex. That code might never get removed, even once we realize it wasn't the real fix. And because you introduce new code, you might have even added a brand new bug to our code. Wrong fixes are really dangerous. So, bugs are not ideal, but they're also very much the standard. But make sure that your fixes are the right thing when that happens. So, some quick final thoughts. Remember that yes, this stuff is about, a lot of this stuff we'll talk about today is about the technical strength, but more broadly, it's finding people who will be successful at that company. So technical skills matter, they're important. But don't forget about behavioral stuff. And also don't forget about your attitude during these problems. There's plenty of people I've interviewed who were very technically strong, but I interviewed them and I just thought they were jerks. And I don't care how smart you are, I'm not gonna hire you if I get that impression from you. So, broadly, it's about finding people who are successful, and that's not solely about technical skills. Okay, so I can stay for a few minutes and take some questions. These horribly washed out, but very pretty handouts in real world. You get those at cracklingcodinginterview.com. I also have a little mini version as like a booklet. I think I might actually have two different things out front where I'm also selling books with, I take credit cards. I don't have a ton of copies, but I have some copies of the PM interview and the coding interview one. Yeah, if you need more stuff on Big O, there's a big section, Cracking the Coding Interview on that. in the 6th edition. There's hints in that book. Don't, as I said earlier, push yourself through problems. Don't just like look at answers all the time. That's not that useful. So really push yourself through problems. And yeah, questions. Yeah.
We have a microphone.
Oh,
Sorry.
he's got a mic.
Cracking the tech career, were you going to be going over any of that during the Silicon Code Camp?
No. So the difference in the three books are coding interviews about coding interviews, PM interviews about PM interviews, plus a good chunk of content about like how to become a product manager, what do they look for, things like that. Cracking the tech career is more of a broader like how to get a job at a top tech company. So it's not specifically for coders, although it has some stuff there. It's targeted people who are either like a programmer at maybe a B or C tier company who wants to go up to the A tier, or jumps up in prestige, or somebody who's like a marketer for an insurance company and wants to do marketing for a tech company. But I do that is on sale on Amazon, but not out. I don't have it in copies here. Other questions? No? Okay. I will be outside if you have one-on-one questions you want to ask, as well as signing books and that kind of thing. Thanks.